today we want to talk about center of mass, or centroids. And centroids are not the same as center of mass. Rather, a centroid of an object is the center of mass if you assume that the density is uniform. If you have a constant density overall on the entire thing, then the center of mass is what you call the centroid. All right, so let's start with some very easy ones. Suppose you had a point mass at 1 kilogram, and another point mass of 1 kilogram at 0.3. What's the center of mass? 2. Because it's just the average of these two, right? So if you imagine that these two are connected by a very thin rod, and if you wanted to balance this over a certain point, the point that you want to put the balance is exactly at 2. It'll be balancing, right? Now, what if instead of having 1 kilogram here, if you had 4 kilograms, what would be the center of mass this time? Do you know how to calculate that? I mean, you probably learned this in Physics 1, and you calculated it by using the torque. So you wanted to know a certain point where the two torques are balancing each other. That's how you figured out the center of mass, right? But there's a quick and easy way to figure it out. Do you know how? You take 1 kilogram multiplied by the position 1, right? Plus 4 kilograms multiplied by 3, the position 3, and what do you divide it by?
3.
The entire weight. So this is what we call weighted average, right? If you take the weighted average, you get the center of mass. You know how to do a weighted average, right? If sports is like 1 credit, but math is 4 credit, and you got like failure of one, and so you got 1 point from the sports, but you got a B from the math, which gives you 3. And then what's your grade point average? Well, how do you calculate it? You do 1 credit times 1 plus 4 credit times 3, and you divide it by the total number of credits, which is 5, right? That's how you calculate the weighted average. You've done this before, right? So you know what it is. And I'm saying that weighted average actually gives you the center of mass. That's how it works, okay? Makes sense, right? All right, next, what I want to do now is to actually do a leap from this easy stuff to something much harder. So how would you find the center of mass for a 2-dimensional shape? So suppose, I mean, this is what I want to do. Suppose you have a half disk of radius A. So this length here is A. This length is A. So it's a half disk. How are we going to calculate the center of mass? That's the question. There's a formula. Actually, if you have taken statics, look at your statics textbook. Some of you are taking engineering dynamics, right? If you have the textbook for statics or dynamics, they use the same thing, right? Same textbook for both, right? Go to the appendix and look for this half disk. You'll see a formula for the center of mass of a half disk, okay? Now the great thing that we're going to do today is to actually derive that formula. Over in that class, they give you the formula without explaining how they got it. Now today we're actually going to get it, okay? So that's the cool thing about today's class. Right? All right, so let's think about how we get it. First, I'm going to think about this entire thing as cut up with two very, very tiny little things. So just think about a very, very tiny thing here, whose area is what we call dA. And then if I multiply the density to the area, I get the mass. Now here's the thing. We are more used to thinking about density as mass over volume, which is called a volume density. But if you have a surface-like thing, it's better to divide the mass with respect to the area and talk about surface density. So that to recover your mass, you multiply the density to the surface. Now when it comes to thin things like a wire, and you want to talk about the mass of a portion of a wire, in that case what you do is you divide the mass by the length, and that's called the linear density. Okay? I think usually people use sigma for the surface density so that you can avoid confusion between the two, but I'll just stick to rho. Rho is the density. Density times the area is going to give you what? It'll be the mass, because the rho that I'm talking about here is the surface density. So this is actually, this much here is actually dm. It's actually the mass of this very, very small portion. That's what we're going to do. Okay. Now, let's go back and see what we did over here. We had a mass. Right? What did we multiply it by?
Position.
The position, the x-coordinate, right? And then, by the way, we really just need to know the x-coordinate of this object because we already know the y-coordinate of the center of mass. What is it? It'll be 0, right? Because the center of mass, because this is symmetric, I know that the center of mass must be somewhere here. Right? And any point on here has y-coordinate 0, so we already know that the y-coordinate of the center of mass is 0. We don't have to calculate it. You can just use the physical intuition to say it's 0. Okay? So the only thing that we care about is the x-coordinate of the center of mass. And according to what we did previously, it looks like the right thing to do is to take this mass and multiply by the x position of to the mass, okay? And then I have to add up this. How do you add these small things? You do integration, right? So you integrate. So I add up all this, all the x values multiplied to the mass, and I integrate over this half disk. Okay? Now, what do I divide it by? I have to divide by something, right? What do I divide it by? How do you calculate the mass? It's just density times dA, and if you integrate it, that's the mass, right? Huh?
Unit vector.
It's like, I mean, you're talking about unit vectors. Unit vector is also divided by its size, so there's some similarities there. Okay? But this, I claim, is what the x-coordinate of the center of mass is, okay? And I want to limit our discussion to the case when the density is constant, so you actually have the centroid rather than the center of mass. This will be the most generic formula, but we want to limit our attention to just the centroid. So in that case, the density is independent of the position x or y. Therefore, we can bring this outside the integral. Okay? If I bring this outside the integral, because these are constants, what can we do? We can cancel them, right? And then look at what this is. If you integrate dA, what do you get? The area, right? If you add up all the small chunks of the area, we get the area of the entire thing. Therefore, the formula that we're going to use will be the following. X bar is 1 over the area times the double integral over that region of x dA. And that's informative enough for you to figure out what's the formula for y bar. What do you think the formula for y bar is? And although we are writing it like this, when you see these formulas, you should really think of it as a weighted mean. So what are you really doing here? I'm taking x, and because I'm adding them up over the entire region and dividing by the area, at the end of the day, what I'm getting is the average value of x. That's why this is considered as the centroid. So if you take that view, it just makes sense. Okay. Now, in three-dimensional space, you can do the same game. The only difference is instead of these integrals, what would you do? Triple integrals, right? And how would you integrate? By dv, and you would divide it by volume. That will be x bar. That will be x bar, okay? And then same thing for y bar and z bar, okay? 1 over v, triple integral, y dv, and 1 over v, triple integral, z dv. But you don't really want to memorize these formulas. You just have this intuition that if you add up all the x values and divide it by the volume, what are you effectively doing? You're taking the average value of all the x coordinates. And that's what we call the x coordinate of the centroid. And if you have that intuition, then you don't really have to learn anything new. It just makes sense. Okay, back to our question. Let's actually do the computation. So our goal is to find the center of mass of this object, radius a, half disk. And the only thing we need to calculate is x bar. Let's try this. We need to divide by its area. What's the area of this thing?
1/2 pi r squared.
Right. So pi r squared is the formula for the circle, but our radius is a. And because it's a half disk, we need to put a 1/2. So that's what we're going to put over here, 1/2 pi a squared. We're using this formula here, with area being that. And then the integral would be over the half disk of x dA. Okay. Another thing I want to do is to figure out what to use for dA. What should we use? dx dy, dy dx, r d theta? Which one? Which is the most convenient one? R d theta. Why? Why do you think so? Because it's a circular region. For circular region, the polar coordinate is the best. It makes the computation most easy, right? So it gives you the easiest computation. Okay? So let's try that. 1 over 1/2 pi a squared. I have r d theta for dA. What do you write for x? How do you represent x using r and theta? R cosine theta, right? R cosine theta. Remember, what's x? X is r cosine theta, and y is r sine theta. R squared is x squared plus y squared. Theta is tangent inverse of y over x, plus some plus or minus 180 degrees in some cases, right? So these are the basic formulas that you have to know in order to convert or write down polar coordinate equations. Okay, so this is what you write. Okay, what about r? R goes from where to where? So if you draw any kind of ray, you start painting from here to there. Right? Where do you begin? Where do you end?
0 to A.
It'll be 0 to A. It'll be 0 to A because any ray that has any overlap with this region will always begin at 0 and it'll end at A, regardless of this direction, right? As long as you have some overlap with the region that you're trying to integrate, this is what's going to happen. Now, what about the angle theta? Where does it go from where to where?
3 pi over 2 to pi over 2.
Okay, so I do agree that this is 3 pi over 2 and pi over 2, but it's not good to say 3 pi over 2 to pi over 2 because if it's 3 pi over 2 and you're going this way, it's increasing, right?
So negative?
So it's better to use negative pi over 2 until pi over 2. If you do that, then it covers the entire thing, okay? So either you do this, or if you really want to use 3 pi over 2, you should rewrite this as 5 pi over 2 because that's the next angle that you stop if you started with something more than 3 pi over 2. Okay, so either use this or use this to 5 pi over 2. Okay, so we're going to put negative pi over 2 to pi over 2, and we compute this, and that's going to give us the formula that you find in your statistics textbook, right? Let's do it. Okay, first, r times r, what's that? r squared. If you integrate r squared by dr, what do you get?
R cubed.
You get r cubed times 1/3. You still have cosine theta, and you have to plug in a and 0. You still need to integrate from negative pi over 2 to pi over 2 d theta. Okay. Plug in a, plug in 0, and you subtract. But if you plug in 0, it's 0, so you only have to plug in a. Let's continue. Let's write it over here. Plug in a. So we get 1 over 1/2 pi a squared integral from negative pi over 2 to pi over 2. And you have 1/3 a cubed cosine theta d theta. Okay. So now you just have to integrate cosine theta. What do you get if you integrate cosine theta? Be 1 over 1/2 pi a squared times negative, no, it's positive sine theta, right? Yeah. So, yeah. It's positive sine theta, and then you have to plug in pi over 2 and negative pi over 2. All right, that's just a constant, so let's pull it outside. See, 1/3 a cubed is just a constant, so you only have to put these in there and subtract, okay? So if you plug in pi over 2 to sine, what do you get? Sine pi over 2 is 1. Sine of negative pi over 2 is negative 1. So you subtract negative 1. Let's see. That's 2, right? And then, let's see. I don't like this 1/2. I should multiply 2 at top and bottom to get rid of this 1/2, right? And this is 2. 2 times 2 is 4. So 4 pi a squared is what you get in the denominator. You have a 3 there. And you have an a cubed. Oh, and you can cancel the a squared with a cubed to give you just a single a, right? So at the end of the day, what you're getting is 4a over 3 pi. Okay? So that's what you get. So in other words, if you had a radius 10 meters or 10-foot half disk, so you had a 10-foot half disk, okay? And then means A should be equal to 10. Where is the center of mass? 40 over 3 pi. That's about 0.4, 4 point something. So like, let's say 4.4, about 4.4 feet from this side, you have the center of mass. So that's the result that we found out. Do you have any questions?